Okay guys, so let's get started. Yesterday we were doing stresses in beams. We just refreshed our memory about flexural stresses. Flexural stresses are developed due to the moments applied, or those loads which are perpendicular to the axis of the beam. So in other words, to the longitudinal axis of the beam. So in other words, if we have a longitudinal axis of a beam and a load which is applied perpendicular to this longitudinal axis, that will induce flexural stresses in the structure or in your beam in this case. And these flexural stresses can then be determined using engineer's beam theory or either beam theory or flexure theory, whatever you want to call it. The flexure formula is stress is equal to Ey by rho. That's what we derived previously. This flexure formula is based on it is actually based on some assumptions which we discussed. Most of the important assumption was that the plane section remained plane. And what benefit that give us? That is really clear from this figure. What happens is that because of the plane section remain plane assumption, you can assume that this line is the line AB is parallel to C prime D prime. Okay, and in other words, the assumption plane section remain plane makes us take 2 points within a beam which we call BD. I think so for some reason we don't. So So the assumption of plane section remain plane helped us to first of all take 2 points which are reasonably close to each other, and these two planes we call AB and CD, and we say that after bending the plane section still remain plane. So AB and CD are still straight lines. Okay, and then that means that we can then make use of trigonometry to simplify our equation. In other words, because of the assumption of plane section remain plane, we assume that we draw a straight line corresponding to this plane section AB, and we assume that this other line, which is OD, is a sort of a transversal. Okay, so OD is also a straight line, and then our d theta becomes so we can make d thetas equal. Why? Because of the corresponding angles. So what I mean is that the assumption of plane section remain plane has helped us to consider these two planes as plane after flexure action. Okay, and that's why we could draw lines parallel to it, perpendicular to it, and we could use the trigonometry to get a simplified form of our equation. Do you understand the significance of plane section remain plane in this? So now today what we are going to do is we will make our way forward towards satisfying the equilibrium equations. Now there are 6 equilibrium equations. What are they? Summation of all the forces in 3 directions must be equal to 0, and summation of all the moments in 3 directions must be equal to 0. So what I have given you is a 3D view of the same beam. Okay, this beam has got 3 axes, as you can see, X, Y and Z. These are the 3 axes, and we have to make sure that the sum of all the forces and moments are satisfied, okay, then this structure will be stable, stay safe in the position, okay, and we would be able to apply the laws of mechanics. So first of all, summation of Fx must be equal to 0. So all the forces which are in the x direction must be equal to 0. So what does that tell us? What are the forces in the x direction?
Stress X.
So we have stress xx, okay, stress xx times dA. So what we say is we assume a small element within this whole cross section, and that element is having area, a differential area dA. Okay, so that element, so assuming that stress xx is the axial stress in this element. How do we know that there is an axial stress xx on this element? That how do we know? Because we have got a beam, okay, and we have assumed that the beam is made up of fibers, okay, and all the fibers except the fiber on the neutral axis are either stretched or compressed. So that is, so stress xx can either be in tension or compression, but we have assumed that for this GH fiber is in tension. So assuming, so this is the same GH fiber which we have drawn over here. Okay, you are seeing the cross section of this GH fiber, and this has got stress X applied to it. Why? Because it is under tension, so there is an axial stress, axial force on it. Okay, so therefore we have stress xx dA. So summation of Fx must be equal to 0. So summation of all the forces in the x direction must be equal to 0. So what do we have? We have stress xx into dA. That is the summation of all the axial stresses in the beam, okay, into dA. So this summation means that we are integrating it around the whole cross section, and this is for all the slices. So stress xx times dA is equal to 0. Why have we written 0 over here? Because there is no axial force applied externally. We are assuming that there is only one force. Imagine there are forces which are only applied on the longitudinal axis. Okay, so you can have something like this. Okay, so there is no force in this direction applied. That's why we make this 0. Now, so from our yesterday's discussion, stress xx is actually equal to Ey by rho. Can we write that? So let us plug values, which is now. What are those items which can be taken out of this integral? We have E, which is the material property. The integral is actually dependent on dA, okay, which is the area. And area means it is all the variables which are related to area, like width, like height, depth, yeah, those are related to areas, isn't it? So those variables can't be taken out. The other variables can be easily taken out. They are like constant for this integral. So what we are saying is that E can come out. Why? Can Y come out? The answer is no. Why? Because Y is a dimension of this area. Y is the dimension of this area. That's why Y can't come out. Y, if you keep on changing your Y, your area will keep on changing. So Y is a dependent variable. So therefore Y can't come out. Rho, which is the radius. A radius, this is the radius, what is called the radius of curvature. Okay, and this radius is dependent on area. The answer is no. Why? Because this radius will be constant for particular area. This radius will be constant for particular area. So we have taken, so what we are saying is, this is your area, okay? This is the area of the cross section. This is the area of the cross section. And this radius of curvature will be constant for this area of cross section. Your area initially is like this, and now it has become like this. Okay? So the radius of curvature stays the same. It's not, if you keep on changing your area, your radius of curvature doesn't change. Okay? And similarly, if you change your radius of curvature, area doesn't change. So therefore, radius of curvature is a constant for this integral. Do you have any question? Do you understand why radius of curvature is a constant for this one? So we can bring E and rho out, and now YdA equal to 0. That's what we get. Now what is YdA? What does this integral tell us? This integral is saying that if you divide this area into slices, okay, small slices, okay, and take a lever, and every slice is located at distance y from a particular axis, okay, then the integral of all those slices is equal to 0. In other words, what I am saying is that if I divide this area, imagine into infinite slices. Some slices are at the top, some slices are at the bottom. Okay? Now, I take, imagine the first slice is A1, dA1, and it is at a distance y1. The second slice is dA2, and it is at a distance y2, and so on and so forth. Then you come down. So if we have a dA1 at the top, we have a corresponding dA1 at the bottom, but the lever arm is minus y1. Yes? And similarly, so if we have these slices, which is dA1 at a distance plus y1, and then dA2 plus y2, let me write it. So dA1 and the distance is plus y1, and similarly dA2 and the distance is plus y2, and so on and so forth. And similarly, we have got a mirror image at the for the area which is under this axis, and that is dA1 minus y1 and dA2 minus y2. So we add them up and we will get 0. So clearly this is the definition of a neutral axis. Neutral axis is that axis which divides the area into two parts in such a way that you take that area portion, that area which is above that axis, multiplied by the lever arm, some lever arm y1 bar, that should be equal to the area below that axis, multiplied by the lever arm which is minus y. Do you understand my point? So imagine this area which is above the neutral axis, that is A1, and this area which is below the neutral axis, that is A2, and this A1 is located at a distance y bar from the axis above, so A2 must be located at a distance y bar. Okay, so A1 y bar must be equal to A2 y bar. Then that would be the definition of a neutral axis. Do you understand my point? So this is easy in the case of rectangular beams. In the case of rectangular beam, it is easy. You can understand. But what happens if your beam is, say, a Z purlin? A Z purlin. Imagine this is our Z cross section, and we have are these the neutral axes? Using this equation, are these the neutral axes? The answer is no. Why are these not the neutral axis? As I told you, that for the neutral axis, the axis which I have drawn, for this axis, you should be able to divide the area into, for example, two parts. Okay, in such a way that you take that one part, multiply that with the lever arm with respect to the neutral axis, and then you take the other part, multiply that with the lever arm. They must both add up to 0. Now you see, just work it out. This area A1, this area is plus A1 multiplied by Y1 bar. Okay, this area is in which axis? Positive y axis. This area. So my point is that you have imagine this is my z axis and this is my y axis. So this is positive quadrant, this is then positive y and negative z, this is negative z and negative z and negative y, and this is positive z and negative y. Now over here the area is, what is the area? The area is this multiplied by the thickness. Okay, and so what will be the centroid of this? The centroid of this is somewhere, imagine, over here. That will be the centroid of this area. Okay, is that okay? And the centroid of this area will be over here. So what? So if you have a centroid somewhere over here, it is located on this side, and you have another area which is located on that side, then what does that tell you? The centroid, look at this area which is above your z-axis. Okay, let me draw another one and to clarify what I am trying to get. This is my another axis, and we have a channel section. The only thing which is different in these two is this one is located on the other side, Okay, and this one is located over here. So this, in this case, is the z-axis a neutral axis? Is this z-axis the neutral axis? And in this case, is the z-axis the neutral axis? That's my question. My question is that among these two, is the z-axis neutral axis in both of them? Or in the top, it's not, and in the bottom, it is. Or it's none in both of them. Bottom one is, yes, the bottom one is in neutral axis. Why? Why is that neutral? Because the bottom one is the mirror image of the top one. The top section is the mirror image of the bottom one. So this is a neutral axis. So if you take VA, okay, multiplied by y bar, that will be exactly equal to this one. If whatever is above is below. Okay, I mean the dimensions are the same above and below. In here, what happens? That the neutral axis, this is not the mirror image of this one. So this is not the neutral axis. For this to have a neutral axis, you have to rotate these ones in such a way that the area times y bar is above the axis is equal to the below axis. Can you distinguish between these two problems which I am saying? I'll repeat what I have said. I have told you that for this equation this equation will always be satisfied for any cross section. Okay? For any cross section, this equation will always be satisfied. The problem is we don't know where the neutral axis is. The neutral axis might not necessarily be always horizontal and vertical. In this case, it is horizontal and vertical. But you can have sections, cross sections, where the neutral axis is not horizontal and vertical. Why? Because you see, if you slice it in this direction or you slice it in this direction, yeah, this is it's not the mirror image. It's not the mirror image about that axis. So you see, the top one is not a mirror image of the bottom. And if you see over here, this one is not the mirror image of this one. Okay? This leg is over here and this leg is sticking over there. So clearly, these two axes are not the neutral axis. So these two axes, you have to move them in such a way that whatever you see above is exactly the mirror image of whatever you have below. Okay? When I say mirror image, I mean that the area which is above times y bar is equal to the area times y bar. The y bar area times y bar. So in other words, the area which is above the axis times the lever arm is equal to the area which is below the axis times the lever arm. That's what I mean mirror image. So I have to move it in such a way that every cross section will have the neutral axis. But in this case, it will be slightly inclined. So you have to move your axis in such a way that your area times y bar above the neutral axis is equal to area times y bar below the. And similarly, in this direction, okay, area times y bar is equal to area times y bar below. So that's what we have to see. Okay, so why am I emphasizing on this one? Because we will be dealing now with these type of structures. You will see that in shear center, we will be dealing with this type of problems. So that's what we have in the summation of fx is equal to 0. Okay, do you understand? Summation of fx is equal to 0. Any question about summation of fx is equal to 0? Okay, now we do, I'll rub it off.